Morning, my dear students. Let's welcome to this session. Last session we have solved a semicircular arch of two hinged in nature applied by UDL on its horizontal span, total horizontal span. Right. In this session we will see a bit different problem. An unsymmetric case. Last two cases, if you observe, we have seen two symmetric cases where the arch is symmetric. Now we are going to see an unsymmetric case. If you observe this diagram, what is given here, to the left of the crown, you have a point load at a distance of x. Right, whereas to the right you don't have a load, so it is unsymmetric. About this crown, it is unsymmetric, whereas geometry is symmetric but the loads are not symmetric. Right, so this is a given problem. To solve for this, okay, so you can start solving it in a regular fashion. Determine horizontal thrust developed in a semicircular arch of radius r subjected to concentrated load P at the point D. Okay, right, it's okay. So we will start solving for H. We will write the formula for H, and then we will start solving numerator first, then denominator. Denominator is same as earlier because it is also a semicircle. Okay, so denominator value will not change, only numerator value you should concentrate on. So what is the change from previous examples to this example when you have unsymmetry in this? Right, what do you have in numerator to write m dash? Okay, so if you want to write mx equation for a beam, okay, so you have a beam of this dimension. Okay, I'm drawing it here itself, the beam. You have a beam, for example, and you have a load here. Okay, right. So now how many equations you write for solving this beam? Okay, to get the complete profile of bending moment of this beam, you should be writing mx equation between AD and between DC and between CB. Okay, and, if it is just a beam, we will go with the two moment equations, one in AD and another in BD. Why C has come into picture? Because you are writing the moment equations for the arch, where your integration process involves the total arch. Okay, so what do you need is between A and C and between B and C, you see the moment equations how they need. Right, between AD you need one moment equation that will be satisfying the portion AD, and between CD you need one more equation, and whereas between BC and you need one more equation. So three moment equations are required for evaluating complete numerator value. Okay. Now, instead of doing that, if you think a little bit different, convert the given problem into symmetric case if it is possible. So convert it. Otherwise, you have to work out by writing three moment equations. It's inevitable, right? So let's see that. Okay, right. Okay, so uh, we try to convert this uh, to a symmetric problem. Let us try that. So to simplify the solution, convert the given problem to a symmetric arch by applying a load P symmetric to the given load. Okay, which means you have to add one load like this. It's at the same location. So given load is at an angle of alpha from the crown to the left of the crown. So I add to the right of the crown at the same angle, the same load. So now it is the same as symmetric case. So this is the final one. Okay. So now if you take a section at C, now you see to the left of C, to the right of C, everything is symmetric. Load is symmetric, geometry is symmetric. Okay. So we have converted the problem to a symmetric case, right? So now the horizontal thrust that you get from this diagram, the third diagram, is not the value that you want. Okay, see, you want, this is your given problem, you want h for this problem. You have modified this problem by adding another load yourself. Okay, and you made this diagram. Now this is symmetric, and now I will work out this problem by taking this diagram, and what I get is here is twice the value of h what exactly I want. Okay. Now you may ask me why it is twice that of the h. Okay, right. So it is h, right? So if you imagine that this is a problem, okay, the given problem, you worked out and you got some value of h. The same way you work out this problem also. Now you can see that these two are just mirror images. Nothing has changed. Span not changed, rise not changed, load value not changed. The location of the load is, here it is to the left, here it is to the right, just mirror images. Okay, so the horizontal load value will not change, so it is h only. So now what you have, h if you have one load, so h if you have another load, so finally your load will become 2h if you have two loads, because you are adding these two cases and you are finally getting this one. Okay, so solving this problem and getting 2h, finally your answer will be divided by 2, that is h value. Okay, so this is how the plan of solving a two hinged arch for horizontal thrust if it is unsymmetric in terms of loads. Okay, right. Let us proceed by taking the third diagram. Okay, right. Now let us consider the arch with two loads, which is a modified diagram. Okay, for simplicity in solving, instead of writing three moment equations, it is only to write now only two equations, between AD one equation, between CD another equation, and it is same to the right. because it is symmetric, so I can use twice that of the value. So that is a plan. Okay, so right. Okay, this is a formula for h. It is very regular formula which is already used. As a is constant, you can just cancel it out. So what is required now is to write m dash values. Okay, let us see how to write. So first consider uh, the section between 0 to alpha. What is 0 means? Alpha 0 means crown, right? I mean to say, so if you take any point on this, okay, so that is going to make an angle of theta at center, right? Theta is a variable, alpha is a fixed value because load location is fixed. Theta is variable. Theta can move from 0 to alpha and alpha to pi by 2. So theta is a variable, remember, but alpha is a constant. Okay, for a given problem and given location of the load. So theta 0 means crown, theta alpha means the position of the load. So for theta is equal to 0 to alpha means you are taking a section between CD portion. This is for portion CD. Let us say like that. Okay. Now what you write for m dash? So sum of all moments to the left of this point. Okay. So what loads you have to the left of this point? What is total vertical load? P plus P, 2P. Okay. And VA, VB are same in values, same in the value because what? It is symmetric. So VA is equal to VB. So finally, the reaction should be half of total load, right? What is total load? 2P. What is half of that 2P? Is P only. So vertical reactions are simply P and P. Okay. So sum of all moments to the left, what do you have? There is support reaction P and applied load P. Okay. Right. Now you write moments from these two loads. Okay. So first P into X. Okay. So what is X now? The location of the section. Right. So this is X. So P into X is going to be clockwise positive minus this load, applied load P into the distance between the load and the section. I shall remove that excess line up here. Yeah, it's a technical error. Don't mind. Right, this distance we want. How do you get it? Okay, that's the question. Right, so let us see what is it here. Okay, P into, if you want this distance, right, just join this line here. Okay, so what do you have that there? This distance you want. Okay, right, so if you join that to this completely and join this point whatever is selected to the vertical line. So now I think you get a point why we take those two lines. Right, what is the value of this one from the triangle? You see from this triangle, what is this value? r sine alpha. The subtended angle is alpha in the triangle, right? So the opposite to this face, the angle is alpha. So r sine alpha. Then what about this value? In that triangle, the subtended angle is theta. The opposite side of theta you want now. So what is it? Again, r sine theta. So if you deduct the r sine alpha and r sine theta from r sine alpha, what you are going to get is this distance. That is what you want. Distance between load and the section. Okay. So that is how it is written, right? So this is m dash for a section between C and D. Means what? 0 to alpha. Theta varying from 0 to alpha. Okay, right. Now to substitute in terms of to substitute for x, what to write for x. Okay, this is all is earlier expressions. We will repeat them, right? Y is r cos theta, ds is r d theta, all that. X is r into or r minus r sine theta. All that we will simply replace. Okay, right. Now let us proceed to the. This is all simplified. You substitute for x r into 1 minus sine theta. P is now replaced with that simply by expanding this term. Okay, so what you have it here is PR into 1 minus sine alpha is the value of m dash, uh, which means moment at a section. Okay, right. So next we need another section to cover half of the arch. By that we make 2 times because of symmetry. Right, between AD I am going to take another section. So what is that? Theta now. Okay, this is the section taken. Okay, now this is your theta value measured from vertical line. This is your theta value. So theta is equal to alpha means point D. Theta is equal to alpha means it is point D. Theta is equal to pi by 2. Means what? Which point? It is point A, springing point. Okay. So now by varying theta from alpha to pi by 2, you are moving from D to A. Remember? Right? That is how you are covering this remaining portion of the arch to the integration. Right? So alpha to pi by 2, varying from alpha to pi by 2. What portion it is? Portion AD. Okay, right. To write moment equation, sum of all moments to the left of this section, there is only one load. Now your x is to be modified. All that worked out earlier, you need to know to you have to erase it. Okay. So because the location has changed, the section location has changed. So this is a location. So this is x. Now this is x. So P into x is the moment. Only one load, one value of moment. And again x is to be replaced by r into 1 minus sine theta, very regular expression. Okay. Right. This is how we write moment equation for portion AD. Okay. Now coming to the numerator evaluation. Okay, so numerator is finally integral m dash y ds theta 0 to pi by 2. It is actually 0 to pi by 2. Okay, but m dash is not same from 0 to pi by 2. You have two values of m dash, one from 0 to alpha 1 m dash value, alpha to pi by 2 another m dash value. Okay, why that is happening? Because there is a load applied between a and c. Okay, there is a point load. That's why the moment behavior is changing once you apply a load there. Okay, otherwise if there is no point load at that point, from a to c you can have a single moment equation. Okay, that will give you moment profile from a to c if you don't have a point load. As you have a point load there at point d, we need to go for two moment equation to completely get a profile of bending moment from a to c. So you have to break at d, a to d one moment equation, d to c another moment equation. That is what is split up here. So 0 to alpha means c to d one equation, then alpha to pi by 2 means another equation, right? So this y twice is written here. Remember, it is symmetric. The other half of the arch is also half of same nature, right? Now it is the mathematical procedure to simplify and get a value of numerator. So substituting for m dash from 0 to alpha, whatever is derived earlier in the earlier slide, that we replace PR into 1 minus sine alpha is m dash value. Similarly, PR into 1 minus sine theta is m dash value between A and D. Okay, this is for portion AD. This is for portion CD. Okay, so to cover A to C, this is what we are planning. From A to C, you have to go. So you are now splitting that into splitting at a point D where point load is there. Okay, got it? Okay. Right. So to proceed for the integration, again substitution method, 1 minus sine theta, we will let it assume that it is t. Then differentiating both sides, it is minus, no, 1 is 0, minus sine theta differentiation, cos theta d theta, and t is dt. Okay, so PR into 1 minus sine alpha into, now what is r d theta into r cos theta. So PR into r and r. So 2 times PR cube is constant. 2 is here, P is here, R, another R, and another R. So 2 times PR cube has come out. Now 1 minus sine alpha and cos theta integration, you have sine theta. So limits 0 to alpha. Okay. So why 1 minus sine alpha is also out of integration? I said alpha is a constant. Okay. Alpha is a constant. So this entire term is constant. So it will be out of integration. So what is remaining inside? Integral cos theta d theta. Cos theta integration sine theta. Limits 0 to alpha. Got it? So this is what? So this entire term is constant. Okay, right. Sine theta, that is the first term. What about the second one? Now you see 2 times P R, another R here and another R here. Okay, this is M dash Y ds. Okay, so 2 times PR cube is coming out here, and what you have integral 1 minus sine theta means what? T. Okay, cos theta d theta means what? Minus dt. So what you have? Minus t square by 2. Okay, so this is what is written here. Right, so first term 2 PR cube, and the upper limit alpha, if you substitute, it will become sine alpha, sine 0 0. So sine alpha multiplied by this term, so sine alpha into 1 sine alpha into sine alpha, sine square alpha. So this is the first term. Second term 2 PR cube, right, minus, so minus is taken outside, t square by 2. What is t now? 1 minus sine theta whole square by 2. Limits alpha to pi by 2 again. Right, so first term remains same, PR cube, right, 1 minus sine theta, upper limit you substitute, then sine 90. Okay, what is sine 90? 1. 1 minus 1, 0. So first term is 0, minus lower limit you substitute alpha, so 1 minus sine alpha whole square by 2. So 2 and 2 is getting cancelled, that's why you don't have 2 here. Okay, so right, so 1 minus sine alpha whole square, 0 minus 1 minus sine alpha whole square, so minus of minus again, it is coming to be plus. Right, first term expanded, so 2 PR cube sent inside, then second term expanded, a minus b whole square, PR cube sent inside. So finally what you have, PR cube minus PR cube sine square alpha remaining from all these. Okay, right, so ultimately PR cube cos square alpha is the numerator value. Okay, right, coming to denominator, as I said, it is semicircle, it only depends on geometry. So integral y square ds is the formula. Y is always r cos theta. So whole square ds is r d theta. This has been followed from example 1 and example 2 likewise. So it is same for a semicircle. It won't change. Okay, unless otherwise you change the geometry, denominator value will not change, because it only depends on geometry, no load. It will not depend on the load, but numerator will depend on the load. Okay, so denominator will depend only on the geometry, means if it is circular, it has to be like this. Okay, right, so 2 times 0 to pi by 2, we take the geometry is symmetric on both sides of the crown, and finally pi r cube by 2 is same as earlier, so it is a repetitive one. Okay, right, so this you have to reproduce from example 1 and example 2 likewise. So in all examples this appears same uh, stepwise working. Okay, and same answer, pi r cube by 2. So what is numerator? So this is explained why we write 2 times h. Okay, so in the initial slide, right, so PR cube cos square alpha numerator, pi r cube by 2 denominator. So 2 times h, This is horizontal reaction of the modified arch to make it symmetric. And what is the answer required for your given question is h value. So that is this one. Okay. So r cube is getting cancelled here. Okay. So divided by 2 goes to the numerator, and that 2 finally is going to cancel out with the left hand side 2. So what is remaining here is just p cos square alpha by pi. This one, p cos square alpha by pi. This is what is the value of h horizontal reaction of a two-hinged semicircular arch applied by a point load at an angle of alpha from the crown, or with respect to vertical. Okay, this alpha is with respect to vertical, remember. Okay, so if you have a load p at an angle of alpha, that is going to be your h value. Okay, even you can now compare with this or check this answer with your earlier answer. You have what problem we have solved? We have solved a semicircular arch, okay, with the point load at the crown. We have solved this case. Okay, this is the first example that we have taken up, and we have got the h value by the similar procedure, which the answer is p by pi. If you remember the first example. Okay, now what is alpha here? Load position, right? What is alpha means? Load position. If the load is at the crown, means if this is a point, if the load is at the crown, what is alpha value? Alpha is equal to 0 degree. Okay, because this is what is alpha you are measuring. Okay, so alpha 0 means this point, alpha 90 means this point. Okay, so if alpha is 0 means load is at the crown, alpha 0, put alpha 0 here, cos 0 1, so 1 into p by pi, 1 square is 1, so p by pi is the answer. So you can also work out like that. Okay, right. So if the load is at some angle, say 30 degrees, what could be the value? If the load is at 45 degrees, 60 degrees, so for all those positions you can easily work out with this single equation. What happens if the load is at the springing point p? Okay, what is alpha value? Pi by 2. Alpha value pi by 2. Cos 90, 0. So h is equal to 0. Okay, got it? So this is how you evaluate a two-hinged semicircular arch with load unsymmetric, concentrated load placed unsymmetrically on the arch. Okay, so you can do this problem by two ways. One is by the taking the given problem as it is and writing moment equations, required number of moment equations based on the given geometry and the load position. So you require 3 moment equations. So what does that mean? You have one more term plus, and one more term appears here if you don't use the symmetry. Okay, you have two terms here, cd and ad, and plus another term you have to include, which is c2b. That also is required if you go in a regular procedure. Okay, regular way, not by these two diagrams. You don't need these two diagrams. If you follow the problem given as it is and taken for solution. If you want to simplify your solution, instead of using 3-moment equations, if you want to use only 2-moment equations, this simplification is required. So add another load of the same location to make it symmetric, and work out only half of the arch, make it twice in the equations. That will lead you to finally taking the modified arch first, solving for the horizontal reaction, which is 2 times the horizontal reaction of original arch. So finally we will end up with the horizontal reaction for original arch. Okay, right. Thank you.